Hello everyone. So now we are going to start discussing about support vector machines. Support vector machines have evolved as one of the very powerful tools of machine learning. There are actually two types. There is support vector classification as well as support vector regression, but we'll be focusing only on support vector classification. Now before going directly to support vector classification, we would start with how someone thought of this idea, how the intuition developed. So there is a very elegant classifier at the foundation of support vector machine. It is known as maximal margin classifier. So today we'll get introduced to maximal margin classifier, and then we will extend this concept to the support vector machines finally. Okay. Now, what is maximal margin classifier? For the sake of convenience, let me assume that we have bivariate data, and so we have two classes. Okay, so let me represent that data by the scatter plot. So suppose I have these are observations coming from first class. Okay, and then we have few observations coming from second class. Now after looking at this picture, what are the things that you observe? First of all, the two groups seem to be fairly separable, right? That is the first thing that comes to your mind. Two groups are more or less separable. So if I ask you, give me a classification rule, what are you going to do? You would perhaps give a line something like this. Assume this is a straight line. Okay. Someone else. So for the sake of convenience, let us assume that we have bivariate data. Okay. Suppose this is first group of observations. And suppose our second group of observations is this. Okay. Now what is the first thing that comes to your mind after seeing this picture? You can see that the two groups are fairly well separated. Okay. So if I ask you, give me a classification rule, you might give me something like this. Okay. Assume this is a straight line. Now someone else might say, why this? I can draw something like this. Some other person might say, I can draw something like this. Assume all these are straight lines. Okay. So these are all possible classifiers, right? Because they are dividing the data into two parts and you are getting 100% accuracy. So entire one group is on one side of the line and the other group is on other side of the line. Okay. So this is how people probably started thinking about developing some classifier which can do this type of job. So first of all, there are few things that we should note down. We are talking about linear decision boundary. Okay. Linear decision boundary in the sense the line which is separating the two classes, it's a line. We are not drawing a curve. Okay. In 2D it would be a line. In 3D it would be a plane. In 4D it would be a three-dimensional hyperplane and so on. Okay. So in general, if you have p-dimensional data, then it would be a hyperplane. Okay. And dimension of that hyperplane is p minus 1. Right, dimension of line is 1. So in 2D you get a line, but line actually is 1D. As soon as you fix x, you get y. So line is actually 1D. So dimension of the hyperplane would be p minus 1. Now just now we saw that there are infinitely many possibilities even when I consider these two classes. So out of these possibilities, which one are we going to select? Because we don't want every person who handles this data to come up with a different classifier. Okay, we have to select in some way an optimal classifier. Okay, so how do we do that? For doing that, we are going to introduce the concept of margin. Okay, so when I have two classes, I would like those classes to be as separable as possible, and hence the concept of margin. Let me try to explain what is margin. See, there are many lines here, and we said that all these are possible lines. So what we will try to do is we will define the margin concept. So let me draw one single line again, and we'll define with respect to that line. Suppose this is one straight line. Now what we will do is we will compute distance of each point from this straight line, perpendicular distance. Okay, and among those distances we are going to locate the shortest distance from each group. Okay, so from this group it would probably be this perpendicular distance, right? Because all the other points are slightly away, and from this group it would probably be this distance. So this perpendicular distance to the line is known as margin. Okay, so what is margin? It is minimum distance, or the shortest distance, perpendicular distance of course, of a point from each group to the classifying line, okay, to the decision boundary. Now what we will do is we would try to maximize the sum of these two distances. Okay, we'll try to maximize this. Because why maximize? Because if someone is near the boundary, if something is near the boundary, then it's likely to get misclassified. Whereas if someone is much away from the boundary, way deep in its own space, then it is a good classification, right? So if I have a point near here, say here, then I am worried whether it is actually in this class and by accident it has come to this class. Whereas about these types of points, I generally don't have to worry. They are well, their depth is quite good. They are well in their own class. Okay, that's why a good classifier would have large margin. Okay, the distance of the point from the classifier should be large, because if it's large, then it means, of course, we are assuming that everything is on the correct side. So if the distance of the points which are already correctly classified is large from the classifier, then it would mean that the classification accuracy is quite good. Okay, hence we need to maximize the margin. Okay, so we would try to maximize the margin. So we would choose that line which maximizes the margin, and that type of classifier is known as maximal margin classifier. Okay, the name is probably now pretty clear. Why the name? So it can be proved that the maximal margin classifier would be the one for whom the margin from both the groups is equal. Okay. Now let us try to formulate this problem mathematically. Whatever we have discussed, let us try to write down in terms of equation. So we said that the separating decision boundary is going to be a hyperplane. So the equation can be written as beta naught plus beta 1 x1 plus beta 2 x2 plus beta p xp. Okay, this is generalization of equation of straight line or plane. So this equal to 0 would be my equation of hyperplane in p dimension, and as I said, dimension of that hyperplane is p minus 1. Okay, so hyperplane in p dimension. Now couple of things. this is not just have you heard about linear transform? What is a linear transform? Linear transform is generally satisfies two properties. So if lambda is linear transform, then lambda a plus b is lambda a plus lambda b. Okay, and lambda ka, if k is constant, can become k times lambda a. Okay, so these are two properties that a linear transform has. But what we have here is not a linear transform, it is an affine transform. Why affine transform? Because it does not have property. In a linear transform, lambda 0 is always 0. Why? Because of these properties. So lambda of 0 plus 0 would be lambda 0, and that would actually become 2 times lambda 0. So this can happen only when lambda 0 is 0. Whereas here, if I substitute 0, 0, 0, I still get beta naught. Okay. So this is not a linear transform, this is an affine transform. But it does have many interesting properties. So our hyperplane is going to be an affine transform in p dimension. Now the equation of that line or a plane or a hyperplane is equal to 0. So for the points which lie on that line or the plane, we get value of this quantity to be 0. But what happens to the points which are not on this plane or not on this line? So let me go back to the straight line scenario. So if you have any straight line, we generally denote straight line by y equal to mx, but you can write it as y minus mx equal to 0. So this is exactly, y equal to mx plus c. So I can write it as, so any straight line I can write as y equal to mx plus c. So it can be written as y minus mx minus c equal to 0. Okay, so this is minus c minus mx plus y equal to 0. So I can say minus c is my beta naught, minus m is my beta 1, and this is my beta 2. 1 is beta 2. Okay, this can be done. Now when you draw any straight line, so this is y equal to mx plus c. On these two sides, you have different signs for this, opposite signs. Y minus mx minus c would be negative on one side and positive on other side, right? So for classifying a new point, this is exactly what we have to check. The sign of this quantity beta naught plus beta 1 x1 plus beta 2 x2 plus beta p xp. Okay. So if it is equal to 0, it lies on that point. However, if it is greater than 0, then it goes to one class. If it is less than 0, it goes to other class. That would become our classifier. Points are on which side. Now in addition to that, we need a margin. So it is something like this. So if this is my classifier, I need some margin here on both the sides. So ideally, this should be greater than some m. Okay. Absolute if I consider, then magnitude wise it should not be just slightly greater than 0, it should be greater than 0 after leaving some margin. So let's say the margin is m. Okay, now let us try to write this down in the form of optimization problem. So what we want to do is we want to find such a line, and we want line or a plane or a hyperplane, and we want to make sure that the margin is maximized. So okay, so this same thing beta naught, this equation greater than 0 less than 0, we can try to write in by introducing classes as minus 1 plus 1. So the two classes we can say are denoted by minus 1 and plus 1, and then we can say that the classification would be good if y naught plus beta 1 x1 plus beta p xp is greater than 0. What do I mean by this? Whenever this is negative, I want it to be minus 1 class so that the product is positive. Whenever this is positive, I want it to be plus 1 class so that the product is again positive. So correct classification can be denoted by this. Okay. And does this line equation of this hyperplane beta naught plus beta 1 etc. Does it have any other significance? Another important point is, if beta naught plus beta 1 x1 plus beta p xp etc. is 0, then any multiple of it is also going to be 0. So what I am saying is, k times beta naught plus beta 1 x1 plus beta p xp would also be 0. So let us try to make use of this property to simplify our life further. Okay, so if you have any, say, plane or a hyperplane or a straight line, let us say you have a plane and you have a point here. How do you compute perpendicular distance of that point from the plane? So if suppose I have some plane whose equation is gamma naught plus gamma 1 x1 plus gamma 2 x2 plus gamma 3 x3, let us say, okay, equal to 0. Then distance of a new point, which is, say, denoted by z1, z2, z3. So you might be able to recall from your high school geometry that distance of this point from this plane would be gamma naught plus gamma 1 z1 plus gamma 2 z2 plus gamma 3 z3. So you substitute that point divided by square root of gamma 1 square plus gamma 2 square plus gamma 3 square. Okay. So can we make use of this? We want margin to be high, and margin we know is a perpendicular distance. So to make use of that, what we will do is, we will combine this property and this property, and instead of just getting a plane which has this equation, we will also make sure that summation beta j square, j going from 1 to p, is 1. What is the benefit of it? Benefit of it is, distance of any other point, when we compute, we won't need this factor because this factor is already 1. Okay. So now, using these things, let me try to formulate the mathematical equation. Things would be slightly more clear when we write it down together. So my maximal margin classifier can be obtained by choosing beta i's in such a way as to maximize m. So maximization is over beta naught, beta 1 up to beta p m. So everything is to be chosen. And what are the constraints? So subject to summation beta j square is equal to 1. Okay. And yi into beta naught plus beta 1 xi1 plus beta 2 xi2 plus beta p xip should be greater than or equal to m for every I in the data set. Okay. What do I mean by each of these things? Of course, we have to maximize m because we are trying to find maximal margin classifier. This constraint we are putting so that this becomes distance of the point xi1, xi2, xip from the plane that we are getting. Okay. If we don't put this constraint, then we will need to put square root of beta naught square plus square root of beta 1 square plus beta 2 square etc. in the denominator. We don't want that. So this is a distance, and we know that margin should be the shortest distance. So distance of every point should be greater than margin, and we are taking yi here, and yi we know is going to be either plus 1 or minus 1. So the sign being positive, m is of course positive, m is margin, and sign of this quantity being positive indicates that we want every observation to be in the correct class. Okay, so what all we are expecting? We are expecting every observation to be on the correct side of the margin, and after making sure that it is on the correct side of the margin, we also want to make sure that so we want to make sure that every point is on the correct side of the decision boundary, and after making that sure, we also want to make sure that it is not only on the correct side of the decision boundary, but also it is at a distance of at least m from the decision boundary. Okay, so if this is my actual decision boundary and these are the distances m on each side, then we want to make sure that all the points are either here or here. Okay, and in the correct classes. Is it okay? So this is what a maximal margin classifier does. Now you can solve for some bivariate examples and see it is pretty easy to find the equation if your classes are linearly separable. Similarly, in higher dimension, if your classes are separable by a hyperplane of appropriate dimension, then finding this is a comparatively easy optimization problem. Okay, so that way this is a very elegant classifier. But of course, many of you might have already thought about some problems. What happens when my classes are not linearly separable? Because they need not always be. So in the next lecture, we will deal with those possibilities. So we are going to extend this to support vector machine, but there is an intermediate step called as support vector classifier, which is also something like soft margin classifier. So this current classifier, maximal margin classifier, is called as hard margin classifier because you are not allowing any misclassifications. Your equation says that this quantity should be positive and greater than m for every I. Okay, so no observation is allowed to get misclassified and no observation is even allowed to be inside the margins. Okay, so this is kind of hard margin classifier. So we'll extend it to a soft margin classifier known as support vector classifier, and then we would further extend it to support vector machines. Okay, you should try to take some linearly separable cases in bivariate data and manually try to work out the equation. Okay, so what are some other interesting properties of this classifier? So through this maximal margin classifier, let us introduce. So if this is my actual decision boundary, this is my margin, this is my margin. So because this is margin, it means that there is at least one point from each side which is exactly at this distance, because if every point is below this, then the margin would get widened. If there is no point on this margin, if every point is say from here onwards, then the margin would itself get widened. Okay, so this is the maximal margin possible, means you have at least one point on this dotted line and at least one point on this dotted line. So the points on the margin, so these lines are called as margins. The points whose distance is equal to margin, whose distance to the decision boundary is equal to the margin, are known as support vectors. Okay, so these points would be called as support vectors. In fact, that's why later we have this terminology support vector classifier, etc. Okay, so support vectors because they are kind of supporting that margin. And once the margin is created, the actual decision boundary is exactly halfway from both the margins. Okay, so once you know the margin, decision boundary is clearly known. Now what are some interesting observations? If support vector gets changed, means if this point moves somewhere, then the margin is got to move, right? So however, if I add a new points here or if I add a new points here, that doesn't affect the support vectors, and as a result that doesn't affect the equation of the classifier. So equation of the classifier is altered only if new points are added which have distance either less than or equal to m. Okay, if there are new points which have distances greater than or equal, strictly greater than m, then equation of the classifier is not changed. Okay, therefore equation depends only on the support vector. Remember, if I add a new point whose distance is less than m, the equation is definitely going to change because margin would have to be shortened and the equation would change. Okay, so the equation depends only on the support vectors. As a result, equation depends only on very few vectors, and hence it is more or less stable. Okay, so if you change a support vector, it might change drastically. However, if you change any other point, it would not get affected at all. So there are two extremes. Okay, so this is another important point, and that would also change as we move from hard margin classifier to soft margin classifier. Okay, for the time being, let me stop here. We will discuss support vector classifiers in the next lecture. Thank you.